Let's begin with a new topic. Means in this lecture we will be talking about the applications of tree data structure. Previously we have discussed some of the definitions that are useful in tree data structures, and in this lecture I will be going to discuss the applications of tree data structure. Okay, but before moving into the topic, let's get some revision of that previous one. So in the first video I have just told that why tree data structure is important for us. Although there are various data structures, but we are using tree data structure mainly because of two reasons. The first reason is that in other data structure we were using the sequential representation of data. We cannot correlate the things in a different way. Means suppose if I have to show a relationship in an organization, in a college, so we cannot do that representation with the help of other data structures. So here tree data structure is very useful. The second main features is this: it mainly represents hierarchical relationship. Okay, so that's the two basic things about the tree data structure. Now, the basic definitions that we have talked about is root node. I've told that the uppermost node is known as the root node, below which all the nodes are attached. Means the topmost the topmost node is known as the root node. Second, leaf node. Node having nothing below them are known as the leaf node. For example, here 40, 5, 8, 30, not 30, it's 70 and 9. These all are the leaf node, below which no nodes are available. Thereafter, children node. Nodes which are below another node is known as children node. Suppose 40 here, the 40 and 5 both are the children of root node 20. So it behaves as a root for 40 and 5. So it behaves as a child of 20. Thereafter, parent node. Node which are above a node is known as a parent node. So like here only, if we see, so these both are the children of node this. Let's suppose A, B, C. So BC is the children of A and A is the parent of BC. A is the parent and BC is the child of A. Okay. Thereafter, we have talked about tree data structure is recursive in nature. So I've told that in order to define it, we mainly call it as a recursive just because it contains subtrees in it. This is a subtree, the left subtree, the right subtree. The right subtree is this. Okay, left subtree, right subtree, and and. Hence, we can call it as a recursive in nature. Thereafter, we have talked about the descendants. What are descendants? Descendants of a node are all the nodes that lie in the subtree with this particular node as root. Look, the descendants of 30. Here, the descendants of node 30 are this 70 and 9. 70 and 9 are called descendants of node 30. Thereafter, we have talked about the degree of a node. Total number of children of a node is known as degree, like A, B, and C. So degree of DOA is equal to 2 because it contains two children. So degree of node A is 2. Thereafter, internal node, tree having no 0 degree or which are not leaf are known as internal nodes. So the internal node can be defined if degree of any node degree of any node is equal to 0. Okay, so it can be considered as a mainly a mathematical representation to see whether if the degree of any particular node is 0, so we can call it as a internal node. Now let us move on to the next slide, in which we will be studying about the applications of tree data structure mainly. So first, the thing that I left in the previous video is ancestors. What are ancestors? A node that is connected to all lower level nodes is called ancestor nodes. For example, we can consider simply the root node, root or ancestor. We can also call it as a root. Okay, because ancestors and root definitions are same. A node that is connected to all l- lower nodes. Here, A is called as a root. We know that, and A can be called as ancestor also of BC. And if there should be a, let us say, there should be, suppose this is anything. Just a second. Suppose this is a node known as E, F. So E is the ancestor of all these nodes. Okay. So here E is the ancestor of all these nodes. See, that is known as the ancestors. Now we are going to discuss the applications of tree data structure. So let's um, uh, take the topic applications. Application of tree data structures. Okay. So the first thing is used to represent hierarchical data. As I have already told that in order to represent a relationship in any college organization, if we want to show a relationship, then tree data structure is mostly used. Okay, so in an organization, it is used in folder structure. Like the folder here simply means that the folder in which we are storing the data in our laptop only. Okay, so that folder is mainly working on the tree data structure because we are compiling every data. Look, you can what we can say, you can make a relationship between different data in a folder, particular folder. So in a folder structure, it is also used XML and HTML context, hypertext markup language. Okay, so it's used there also in object oriented. Of course, in the process of inheritance, tree data structure is mostly used. Okay, thereafter, JavaScript reaches to HTML using tree and manipulate. Okay, so the main thing that is the main point that all the covers is to represent relationship in the different organizations or different languages as well. And the last is much important that JavaScript reaches to HTML using tree and manipulate. Like suppose, and this is the HTML content, this is the CSS content, and this is the JavaScript content. JavaScript, HTML, CSS. Okay. So HTML and CSS could be connected with them also. Means we can directly connect HTML and CSS through various pages and all. But we cannot directly, there is no direct way to connect HTML, CSS with JavaScript. So in that manner, we would recommend to use tree data structure that will directly show a relationship and will connect these both. Okay. So directly they are not interrelated. We have to add tree data structure in order to do that. Thereafter, binary search tree. We would definitely discuss it later that what is a binary search tree. Okay, it's a binary search tree. Let's mark it as a star. We'll discuss it later. Binary heap. These all are the topics that we will discuss it later. Binary heap mainly used to represent priority queue. Be sure about that. Every time it is asked that why binary heap is required, why we are doing binary searching, what is the disadvantage of linear searching. Okay, these all are the questions that arise mainly in the vivas. So what's the use of binary heap? It is used to represent priority queue. Thereafter, B plus trees in DBMS. In database management system, B and B plus trees. Definitely we will discuss this also in the next lectures. For indexing, this is the main thing uh, that is used to focus on. Like for indexing is a process in which we have seen in the row and column measure mapping, indexing is used there. So you can directly correlate from there. So B and B plus trees is used, but indexing is mostly done in database management system. Means while we are creating a database and we are storing our data in it. So at that time we are mainly doing indexing, and this indexing could be done with the help of B and B plus trees. Thereafter, spanning and shortest shortcut path trees in computer network. Like we have networking system. Uh, you might not have studied till now, but like computer network, spanning and shortcut path trees are variously used. Like if I'm telling about a router, that's a mainly part of a computer network only. IPv4. Um, there are various things of the network, internet protocols also. So it's the that's the main part of it only. Thereafter, the spanning and shortcut path trees. The examples of this computer network is bridges using spanning trees. Bridges is not like a real world bridges, but there are various structures that are used to represent this tree data structures, and one of them is the bridge here. So we will discuss this also later. And routers. Look, I have told that about the routers. Router uses shortest path tree. This is the basic important thing that we should know. That router uses shortest path tree means look why router is using the shortest path tree in order to make the range bigger. It uses shortest path tree. We will see the working of a router in the networking section. Okay, phase tree, expression tree in compiler, mainly used to parse the source code. You have to see this thing in detail also, that what is the parsing, how it is done, and how to do it. Okay, so parsing tree, expression tree in compiler, how it is done. So tree data structure used there also. Thereafter try. What is try? This is the very important thing in data structure. It is used to represent directories. Okay, so dictionaries. It is used to represent dictionaries. It also supports functioning like prefixer. Like in various programming languages, we have already standard template library STL. Okay, so try is used to represent dictionaries and also supports functions like prefixer. And in try, it is a mainly part of a tree data structure. Know that much only. Okay. Thereafter, suffix tree used to do fast searching, mainly in pattern searching. Suffix tree is mainly used in a pattern searching. It is a type of tree that is not commonly used or named. Suffix tree is mainly used in pattern searching. Thereafter, binary index tree. These all are the types of tree that we should know. Thereafter, binary index tree used for range query searches. Again, this is the best word to know about, that what is a range query searches. And this topic comes under the searching and sorting. Okay, this process comes under searching and sorting. So we'll discuss their range query searches. And colleges, the teachers do not teach about these all in the depth. Thereafter, segment tree. What is a segment tree? It is used for range query searches, first of all, and is more powerful. Look, binary index tree and segment tree. These both are different, but they are mainly used in the query searches, range query searches. But if we compare binary index tree and segment tree, if we compare this both, so segment tree is more powerful. Okay, it is more powerful than binary index trees because it is faster than segment tree. We'll see the algorithm for both. So hence we can consider the segment tree as more faster than the binary index tree. Hence, they are used for the range query searches. Thereafter, binary tree. A tree in which a node has at least two children, or a degree of every node is at most two. What is the at most? Means it can be two or more than two. For example, what is a binary tree? Look, there's a value 2, 3, 4. So the degree of node 2 or first node, degree of is 2 because it contains two children. Because it contains two children. Hence as a we can consider this as a binary tree. Okay. Degree can be 0, 1 or 2, but not more than 2. This is known as binary tree. Thereafter, here I have means you can see here in the diagram the mainly representation of a binary tree, and if you will make this diagram in the exams, definitely you will get proper marks. This is the basic representation of a binary tree, and this is the linked list representation, I think. Yeah, linked list representation of a binary tree. Here what I have shown, look, this is the root node 30, thereafter children node 40, again left children node 70, right node 50, 60 and 80. So this is the first node, okay, left pointer, left pointer, right pointer, and in the middle the value is stored, info part. Thereafter representing this 40 here as a linked list, and representing this 50 here. Let me do it more clearly. Okay, this 40 is represented here shows that only one child is there, so we have made only one linked list representation, and here 50 we have made two linked list representation, means here at the below. Okay, so again 70 represents one linked list, so only one has been represented, but these are two, 60 and 80. So for both we have represented a linked list. Okay, so this is the basic representation of a binary tree. Now let's move on to the next thing. Why we study binary tree while we can use array tree having n number of children? Again, this is the very interesting questions that are mainly asked in Vivas or everything. So why we mainly study binary tree? Uh, the main biggest answer is that most of the tree data structures, most of the tree data structures are variations of binary tree. Hence, we use binary tree always. Let me give you an example of it. Like in any of the college, this is the college. Okay, ABC college. Okay, he want to hire a person. Hiring is open for teacher for DSA. Hiring is open for DSA. Okay, so now I've received two applications. One from a person, one from a person having experience, having experience of about 10 years. Okay, and second, a person having experience, not experience, fresher. Let us take fresher. Okay, okay. Both have same knowledge. Okay, both have same knowledge. So, what we have done, we have taken an organization a new college. He is hiring for DSA faculty member. So they have got two applicants, one and second. First one is the experienced one, at least 10 years, and the second one is a fresher. So whom did the organization would more prefer? Definitely experienced one, definitely, and he will definitely pay him much better than the fresher. That's the same thing happens here also. That we have other types of trees, but then also we are using the binary tree. That's mainly now you can understand the definition well. Most of the tree data structures are variations of binary tree. Hence, we can use binary tree always. Means we are like if we consider all the trees as a child of binary tree, all the tree we are considering all the tree as a child of binary tree. So we can call binary tree. So we are just studying binary tree only in spite of all the other trees. So simple definition. If anyone asks, will that why binary tree we mainly use, irrespective of the other trees that we have. So just give it a simple answer that uh, we know that there are various types of trees as well, but we mainly prefer binary tree just because of a single reason that most of the tree that we are using is just like a children of a binary tree only, and all are the variations of binary tree. Okay, so now let's see the representation of a binary tree, how it's represented. So in the basic representation, yeah, it's a algo, I think, yeah. So this is the basic root node, the left subtree, the right subtree, containing one node in the right subtree, containing two nodes in the left subtree. So it mainly acts as a root. Now, what we are doing is we are just creating this. We are writing an algo in order to create this structure. So first we are taking a struct node here, taking the struct node, okay, and this is the basic representation of structure. How we represent structure. Struct node, taken the struct node int key. Here I am defining key as a root node. Okay, we will see it later. Later means now only. In the last of the algorithm. So I have taken a basic structure of struct node. Thereafter, I have initialized key as a root node. Thereafter, int key. Thereafter, I have made the left subtree node left here. I have made the left node left node. Thereafter, I have made the right node. Thereafter, made the right node. Thereafter, I am storing the value of k in the node. Okay, storing the value in the node. Thereafter, I am initializing the key is equal to k, means I am again storing value of k using constructor which initializes key as a parameter as null. Okay, so firstly we are taking k is equal to this where it is a null. K is equal to a node containing a value null. So initializing this. Thereafter, left is equal to right is equal to null. Now what I have done, I have created two things. This is null, this is also null. That what I have used here. Thereafter, coming into the main section. Coming to the main section, we have int main node asterisk root is equal to new node 10. Now in the main section, we are defining the values that I want to give root. Here we can see that here we are representing root. So we are storing the value in the root as 10. Okay, now done. Now root roots left is equal to new node 20, sorry. So in the roots left, we have already created a node and we are storing the value 20. Thereafter, roots right is equal to new node 30, making already made a node. Now we are storing the value 30, the right of the particular tree. Thereafter, root left is equal to new node 40. So what does it means? Again, I'm making a node and storing the value 40. So this is the basic algo to make a node. Okay, understand? So this is the basic representation that we have seen of the binary tree. From the next video, we will start the tree traversal. Means in order, pre-order or post-order, these all are the things. So we'll discuss it later. Now, uh, if you have any problem, please comment down your problems. Definitely, we'll share you the notes of all the things that I have uh, taught you till now, and you will get all the proper notes. Okay, so thank you for this lecture. Thank you.